Hello, I'm Sandy Brownlee, and this is some joint work with Jason Adair, Simon Haraldson, and an MSc student of ours last year, John Jabo, and we're all at the University of Stirling in Scotland. The talk follows a pretty standard outline. I'll set out our motivation and what we were seeking to find out before going into the methodology. So in this case, the machine learning models, hyperparameters data and measurements that we were making, and then I'll go into experimental results before we stray into some search-based optimization towards the end. So what's this all about? Well, typically, if we were applying machine learning to a given problem, we would look at a few different models and we would tune their hyperparameters in order to get the most accurate model. And that's usually where the focus lies. It's getting the most accurate model, the one with the lowest error rate on some unseen test data. But there are problems at the extremes of scale, right? And the actual training and the application of the model consume electricity. And we know that data centers are big consumers of electricity. Training a large deep learning model, as a result, produces a lot of CO2. And at the other end of the scale, on embedded devices, remote sensors, mobile devices, we're trying to minimize the energy footprint as much as possible to make use of the limited resources that are available. And we've got a real opportunity here. So with typical genetic improvement applications, we've got a target application that we're trying to speed up or make more energy efficient. But ultimately, we're doing that in the context of trying to retain functionality still. And functionality is quite coarse-grained. You either pass the tests or you don't. But with machine learning, our functionality measure is accuracy. It's on a fairly continuous scale. So there's the opportunity here for us to be able to trade off accuracy in return for getting an improvement in energy efficiency or runtime. I've done a little bit of work on this topic in the past, published in the paper that you can see there, where we looked at a limited number of hyperparameters for a multi-layer perceptron. We found a couple of interesting things. One was if we plot all of the hyperparameter configurations in terms of error rate and energy, we were able to actually do quite well in both low error and low energy consumption. But the relationship between the hyperparameters and energy consumption was a fairly complicated one. So over on the right, you can see as hidden layer size goes up, the energy goes all over the place. So we wanted to find out a little bit more about what's going on. So in this study then, we formulated 5 questions that we really wanted to answer. The first one was just whether there is a trade-off between energy efficiency and accuracy, whether we've got something like the cartoon plot that I've given there, where we go from low energy, low accuracy to high energy, high accuracy, and we're able to kind of walk along that trade-off. And then kind of digging a bit deeper, what are the factors that drive that trade-off? Is there a difference in those factors between energy for training and for inference? Can we spend more energy training for more efficient inference? That'd be really helpful for things like embedded devices or remote sensors, mobile devices, where we want very efficient inference with the final model. We might be able to invest a lot of effort in training that model before it's deployed to get that. And can we make this hyperparameter search more efficient by using search-based optimization? The approach that we took was fairly straightforward. We're using the MLP classifier in scikit-learn and applying hyperparameter tuning to it for the hyperparameters that I've listed there. A mixture of structural ones, things like hidden layer size and the activation function that's being used in the neurons, as well as non-structural things like the solver, the training algorithm that's being used to fit the model. And we applied it to a mixture of UTI datasets, common benchmarks, and a much larger dataset, this mortgage dataset from Kaggle. Our experiments covered a number of different measures, and the full set of results are available at a link in the paper and at the end of the presentation. In this talk, I'll be focusing on accuracy on test data and energy for training and inference. But the things that we measured overall were test accuracies, that is, accuracy of the model on an unseen test set, the 5-fold cross-validation accuracy of the model, the energy consumption of the CPU while the model was being trained, and that was measured using PyRapple, which is a Python library for accessing the instructions on Intel CPUs that can approximate energy consumption for a given process. The CPU time and wall clock time taken for the training process, measured using the Python functions listed there, and the energy and times for inference, that is application of the model to test data 1,000 times. And the reason that we repeat that 1,000 times is basically to make the numbers big enough to be easy to measure, and also to replicate the idea that the model is being applied to new data repeatedly. The training and test runs were repeated 30 times interleaved, so that means for each we will go through each of the configurations once and then repeat each of the configurations again, and so on for each of 30 repeats. That's so that the random variation, random noise in energy and time measurements would impact each of the configurations roughly evenly to try and counteract some of that noise. And we report median and interquartile range because the as you can see, that histogram there shows the energy measurements for 30 repeats of one configuration, and the distribution is definitely not normal. You might be wondering why we're not just using CPU time as a proxy for energy, and anyone who's done energy measurement will know that the relationship isn't as straightforward as that. This is for all configurations on a particular data set, the CPU time versus CPU energy, and you can see that although there is overall a bit of a linear trend there, there's a lot of other things going on too. The bulk of our experiments were in a grid search experiment. That's an exhaustive search over all the possible hyperparameter combinations within specified ranges. And for the UCI datasets, these were quite quick running, so we looked at a little over 1,400 configurations. And for the mortgage data, that was a bit longer running, so we limited that to 72 configurations. And the plots I'm showing you here are the Pareto optimal solutions. So these are the ones for which we can't do better in both energy and accuracy. And we can see that there are very clear trade-offs. So the one on the left is the training energy versus the test accuracy for the mortgage data. And you see at the high end, at the high accuracy end of the results, we've got this solution here, which is quite high accuracy, but we can drop something like a third of the energy consumption of that while only losing a little bit of accuracy here, something like about 0.5% accuracy drop off there, but a massive reduction in energy. The plot on the right is on the GLASS dataset, and it is inference energy versus accuracy on test data, and we see the same kind of thing. So we've got a very high energy, high accuracy model, but we can drop 2/3 of the energy here, and we've only dropped something like 3 or 4% of the accuracy. The next part of the study was a deeper dig into what was driving the trade-off between energy and accuracy. So we created a lot of visualizations like this one, where we have each row being a hyperparameter configuration from the Pareto front, and the columns being features and the energy and accuracy. So we're able to draw out any patterns, things like in this particular one, logistic regression seems to be appearing at the high energy, high accuracy end of the trade-off. To briefly summarize the results, for the test accuracy versus training energy, we found that activation function seemed to have a bit of an impact on the trade-off. So quite often the tan-H function would appear at the high energy, high accuracy end of the trade-offs. Hidden layer size, you might have expected to have quite a strong relationship with energy too, because as you have more neurons in the model, it consumes more energy and it can encode more information. And that was definitely the case for the GLASS dataset, but actually on the other datasets there wasn't a particularly strong pattern there, similar to that earlier work that I highlighted before. The solver, that definitely makes a difference. this is no surprise, right? The algorithm that's used for training the network will have an impact on the energy consumption during the training process and the accuracy of the final model. But we also saw this quite interesting connection where sometimes you're able to get a higher accuracy model with by combining a smaller hidden layer size and a longer training run. So it was still high energy for the training, but the model will be much smaller, less complicated. So perhaps could be lower energy consumption for inference, and that there is a possible route to being able to invest a lot of energy in the training stage, but have a more efficient, lightweight model for inference for, say, a remote or a mobile device. Looking at the trade-offs for test accuracy versus inference energy, very clear pattern there. As the hidden layer size increases, more neurons, we have higher energy cost for inference. And the interesting result there is that the solver still sometimes makes a bit of a difference. Sometimes we were finding the Adam solver was at the low energy, low accuracy end of the trade-off for inference. So is there a difference in these factors between energy for training and inference? Well, yes, there definitely is. I've mentioned a couple of times now this idea that we might invest more energy in training in order to get a saving in inference. So what we did was we tried plotting for all of the configurations on a given data set the CPU energy for training versus the CPU energy for testing, that is inference. And what we can see here is that there is quite a broad spread, although there is loosely a positive correlation between the two. So that sought after trade-off doesn't really appear to be coming through. If we dig in a little deeper and filter those results for the higher accuracy configurations, we can actually see, so these are the lighter colored ones, are the high accuracy ones. The configurations around this area here are both low energy for training and relatively low energy for inference, and we don't seem to be able to do much better than those in terms of accuracy. So there isn't really as much of a trade-off as we might have hoped here. All the results I've presented so far have been using a grid search that is an exhaustive exploration of the space, and I think most of the people in the audience will recognise that we can maybe be more efficient than that by using some kind of stochastic search method. So we tried looking at applying NSGA2 to the same hyperparameter searches. We just used the default configuration of NSGA2 from JMetalPy, but we quite tightly restricted its runtime. So we limited it to a population size of 8 and 240 function evaluations. That's about a sixth of the total search space, because in practice, if we were going to let it run for much longer, we'd just do the grid search and be guaranteed that we'd find the global Pareto front. The objectives for the run were test accuracy versus median training energy over 30 repeats of the training process, and the plot over on the right shows the results for one data set. And we repeated NSGA2 30 times in order to get a range of Pareto fronts. So what we can see in the plot, the dots are the configurations from the grid search, the exhaustive search, and then the line shows the range of runs from NSGA2. The black line is the median Pareto front. This is the area that was reached by at least half of the runs of NSGA2, and then the shaded area around it are the minimal and maximal Pareto fronts, basically the one that was reached by the best runs of NSGA2 and the worst. And you can see there that actually we're getting close to the global Pareto front, but just missing out on it slightly. So there is certainly some potential here for a search method like NSGA2. So to briefly summarise, we've identified that there's a clear trade-off of energy versus accuracy, at least for the models and the datasets that we explored. And you might exploit that in one case by dropping only about 1% in terms of accuracy to save over 3/4 of the energy consumption. We found that both structural and non-structural hyperparameters drive this trade-off. So as well as things like hidden layer size, the training algorithm, the activation functions, these all make some kind of an impact on the trade-off. We showed that a search-based approach like NSGA2 can approximate this trade-off fairly well with far fewer evaluations than a grid search. And of course, there is plenty more to do. We would certainly like to generalize it, look at other model types, random forests, regression models, etc. Look at other hardware architectures, other data sets, and a deeper exploration of the hyperparameters that drive the trade-offs. Certainly more on this question of training versus inference energy. Full results are at the link there, which is also in the paper, and you can reach me at that email address. Thank you very much for your time, and I now invite questions.
Approximation.
Yep, so PyRapple is indeed it's kind of a model that's built into the CPU. I would certainly like to use real power consumption. I've been playing around with a couple of devices to measure the CPU consumption of directly from hardware, but it's not something I've had a chance to do yet. Primary reason for using PyRapple is it's simple. It was just loading a library and away you go. But I would certainly like to look at real power consumption if I can find a way to do it.
Thank you. And thank you, Alex, for the comment about the CPU cache usage. And here a question from Wes Weimer. Can you elaborate or speculate a bit more on relevant non-structural hyperparameters? For example, are there some other promising ones? What do they have in common?
Yeah, so I think people can see us now. It looks like we were missed out at the beginning there. Anyway, yeah, that's a great question. I mean, the obvious things are the choice of training or learning algorithm. So using gradient descent or something else, basically. I think these would be the obvious things. I guess you might be splitting hairs by calling something structural or non-structural, because you might say that the activation functions in the neurons, are they structural or not? Are arguable either way. But yeah, I think the likely most promising one is the choice, the learning algorithm, because that will definitely affect the energy consumption for training, and implicitly is going to change the kind of model that you get at the end as well. So may have an impact on inference, but obviously still a bit open on that at the moment.
Gotcha. It seems there might be some issue on the microphone here, but seems to solve. So let me know if you guys still have difficult hearing us. All right, now we have 2 questions from Bill Landon. First one is, any feel for reliability of a PyRapple? About reliability thing. Amrik has been using instruction count, and I have used nanoseconds. Marcus has measured joules. So that's the first question. You want to go, Sandy?
Sure. I don't have a direct feel for it, which is probably pretty bad. One thing that we really need to do with this stuff is to validate the different approaches. I think there'd be quite an interesting study in comparing the different ways of measuring energy. I know Marcus's stuff where he was. I'm trying to remember if he was using probes or if he was looking at battery count. It was all on mobile devices, and you got crazy results. This is Marcus Wagner. It's published a few papers on this where you see kind of energy consumption on mobile apps are doing this, and it'd be really interesting to try comparing the more model-based approaches with what he's doing. I can see that there's a suggestion for ways of measuring. Eric, thank you for that very much, because I'm certainly wanting to investigate more approaches. So yeah.
The second question from Bill is, any tie-in with approximate computing fast multiply for sigmoid 600?
Oh, great point. Absolutely. Yeah, because I think this is as I kind of said in my opening, I think this is very much an area where we can cope with some error. So let's learn from the approximate computing approaches as well. Throw in the possibility for errors where we're almost well, we're not quite guaranteed, but we've got a much better chance of saving some energy.
Yeah, I think maybe as the host, I have the privilege to ask a question myself. So I remember in your paper, you mentioned that you choose to using a Python scikit-learn library instead of Weka. I'm just curious for future research who want to do this kind of studies, the choice of the machine learning platform or models, would you foresee any effects just because of the choice of that on your results?
Almost certainly. So one piece of earlier work that I did was using Weka, and we got rather different results. I mean, admittedly, I was trying different hyperparameters too, but we managed to minimize energy and error rate, and we got a trade-off here using scikit-learn. One of the things I'm going to try and retread now is doing the same things that I did with Weka in scikit-learn and seeing if there is much of a difference. I mean, in principle, there shouldn't be, but totally different implementations, and there's got to be some differences there.
Gotcha. So I guess the other question is, like you emphasized, that I also recently heard the term called green AI because people started being so concerned about energy consumed. It's becoming a more important topic right now. I wonder for doing research like your work, what are the biggest challenges? What are the hardest part when you're doing the work that you want to let us know? You can prepare for that.
Hardest challenges. One is this whole question around measurement, and actually, it doesn't matter how you cut it. It's a noisy measurement to be making. So how we manage to do that efficiently and reliably, that's a big challenge. And the other side of measurement, which is just physically doing it in a way that's general. I'm looking at using this approach, using PyRapple, which is focused on Xeon CPUs, but that's going to be applicable probably to the machine that I was doing the training on. Trying to come up with a general approach is going to need an investment in a lot of hardware as well.
Gotcha. Yeah. So I'm sure a lot of our audience have also heard of this term called SE for AI. I'm sure that's also relevant to your work. So I know that one big challenge in SE for AI right now is as a software engineering people, how can we even define like a concept like correctness, that kind of stuff. So I don't know, when we apply search-based algorithm to this problem, what are your thoughts on, defining your, let's say, fitness or objective functions if you have one, and also those correctness thing, because it's a totally different area. It's not a normal program.
Yeah, I mean, I think that is the broader point that I'm making, is that the idea of correctness here it boils down to error rate, or accuracy, or whatever precise measure you're wanting to make. But I think where we're talking machine learning and we've got this kind of much fuzzier idea of correctness, I think there is a bit more potential for trade-off there. There isn't necessarily a perfect model, and so let's exploit that.
And also I can see right now in the chat, our audience also provides many very interesting links for papers relevant to this topic. So we have 48 seconds, so let me try if I can actually say what's the comment here. Could this approach be combined with a non-GI sampling or pre-filtering approach for minimizing training data? Sandy, what do you think?
Yes, probably. That's a great idea. I might try that.
Yeah, maybe this sounds something the community can check together in the future. Yeah. Yep. All right, we have 15 minutes.
Great. Thank you very much for the comments. There's some good stuff there.
Right, so to avoid like a hard cut, so yeah, I think Sandy will be there in the discussion room if there's any more questions, everyone. Thank you so much for the questions and the comments and the links.
Thanks.
All right. Okay, I need to go, Sandy, because I'm chairing the next session too, okay? Yep. I think it's a great Q&A session. Oh, wait, should I leave the...